Iterated queue network beyond one-step Bellman updates in deep reinforcement learning. Reinforcement learning is still far away from being applied widely in the real world. This is mainly due to sample efficiency, which means that we need a lot of interactions with the real world to get a satisfactory outcome. In this paper that we published at TMLR, we argue that this is because our reinforcement learning algorithms are still too sequential. Let me explain. Let's take deep queue network, a classical algorithm in value-based off policy reinforcement learning, where a target network and an online network are used during the training. The online network, represented by Q1, is responsible to learn the Bellman update or the Bellman iteration constructed from the target network and with some samples, so R and S prime. So the loss is constructed as follows. It's R plus gamma max of Q minus Q1. And you learn Q1 to basically minimize the distance between Q1 and gamma Q0, which is represented by the red arrow here. After a predefined number of gradient steps, we update the target network to the online network. So the target network that was Q0 becomes Q1, and we learn another Q function that we call Q2. This Q function is responsible for learning the second Bellman update or the second Bellman iteration, which is gamma Q1, which is exactly the same as before, but this time Q1 is here and Q2 is here. And we do that repetitively or sequentially during the training until the training ends. And you can see here that only one Bellman update is learned at each gradient step. Each time we see a sample, only one Q function is learned. In contrast, we developed an algorithm that we call iterated deep queue network that builds on deep queue network, but that leverages another Q function to learn the following Bellman iteration, while the first one is still being learned. Indeed, previously, we had to wait for this function to be frozen in order to learn the following one. But now we are actually learning them in parallel, hence bringing sequential algorithms closer to a parallelization scheme. This means that the Q function here is a non-line network to learn the first Bellman update, but is also a target network to learn the second Bellman update, which means that the loss that we use is simply a very close loss to DQN, but uses two networks, and it's the sum of the TD errors, which are represented by the red arrows here. After a predefined number of gradient steps, similarly to what we did in deep queue network, we shift the window. But here you can really see that multiple updates are learned at each gradient step. And as I was saying, after a predefined number of gradient steps, we shift the window by updating the online networks to the target networks to consider the following Bellman iterations. And we do that until the training ends. This was a window of size 2, but we can also, at the cost of more networks learned, we can increase this window to make it even more parallelized. We tried it in practice on 20 Atari games and 6 Motoko environments. We evaluated deep queue network, implicit quantile network as a stronger baseline. This is on discrete action spaces, but we can do the same with SAC and draw queue in continuous action spaces, where policy evaluation is performed. Those curves were obtained by simply minimizing the immediate loss. However, if we minimize the sum of the losses to learn multiple Bellman updates in parallel, we increase the performances of each baseline. This gives a performance boost in terms of sample efficiency. Thank you for listening. I hope I convinced you that our approach, iterated Q-network, helps parallelizing sequential algorithms. You can find here a link to the code, a link to the paper, and a link to a follow-up work that tries to leverage the richness of this loss to remove the target network. Thank you.